Hey guys, in this video we shall derive the formula for computing double integral over a polar rectangle. Let us start with the definition of a polar rectangle. A polar rectangle is a region on the xy plane such that the polar coordinates are bounded by constants. Namely, the variable r is bounded by two constants, let's say a and b, and theta is also bounded by two constants, let's say alpha and beta. Now, the fact that theta is bounded between alpha and beta means that the region is lying between two rays. One with the equation theta equals alpha, and the other one with the equation theta equals beta. Likewise, the fact that r is being bounded by two constants means that the region lies between two circles, the smaller one of radius a and the bigger one of radius b. Alright, the question is, how do we compute a double integral of a function f of x and y over such a polar rectangle R? Well, first we partition the polar rectangle into smaller regions by partitioning the underlying polar coordinates. So suppose we have the interval from alpha to beta for the variable theta. And let's suppose we partition this into subintervals, each of which has size delta theta. Then the values of theta on this partition will give rise to a collection of rays coming out from the origin that looks something like this. Alright? The first ray here at the bottom is given by theta equals alpha, and the last ray over here is given by theta equals beta. And in between we have many different rays such that the angle between adjacent rays is precisely delta theta. Now suppose we have the partition of the interval from a to b for the variable r into subintervals of size delta r. Then the values of r on this partition will give rise to a collection of circles that look something like this. Notice the smaller circle has radius a and the largest one has radius b. Moreover, adjacent circles must be of distance delta r apart from each other. In other words, if you look at adjacent circles, the difference in their radius is precisely delta r. You follow me? Alright, let us denote a subregion of this partition by Rij. Here the index I comes from the variable r and the index j comes from the variable theta. And let us suppose we have a sample point from this subregion denoted by Ri star and theta j star. Suppose the xy coordinate of the sample point is given by xij star and yij star. Then clearly xij star is equal to Ri star times cosine theta j star, whereas yij star is equal to Ri star times sine theta j star. Alright? Well, notice that the partition we have for the polar rectangle here is not uniform, in the sense that the areas of these subregions are not the same. In fact, the further you go away from the origin, the larger is the area of this subregion. Okay? Well, later on we'll work out the formula for the area. So for now, let us look at the double integral over this region R. If you remember, the double integral over R is roughly the double Riemann sum of the function evaluated at the sample point coming from Rij times the area of Rij. Alright, and we are computing this double sum over I and j, so that eventually, as the partition gets finer and finer, the double Riemann sum will converge to the double integral. Anyway, the point here is we want to convert the x and y to the polar coordinates. So we are going to replace xij star by its expression here in terms of the polar coordinates, and likewise the variable yij star will be replaced by its expression in terms of r and theta over here. And next we are going to calculate the area of Rij in terms of the polar coordinates. Now every region Rij is bounded by two adjacent circles and two adjacent rays. The smaller circle has radius r, and the larger one has radius r plus delta r. So the length on the side of this region is precisely delta r. Now, in order to work out the area of Rij, we shall need to determine the length of this little subarc over here. Well, that is straightforward, because in elementary school we learned that the length of a subarc coming from a circle of radius r is equal to r times whatever angle between the lines over here. Since the angle between adjacent rays is delta theta, so the subarc on this side of the region Rij is precisely r times delta theta. So that will be the length of this little subarc. Next, we are going to approximate the area of Rij. Notice the region Rij is roughly a rectangle when the dimensions are small. Therefore, we can approximate the area of Rij by just multiplying these two numbers, as if Rij is a rectangle whose dimensions are given by these two numbers. Alright? So the area of Rij is approximately delta r times delta theta. And this is the number which we are going to substitute back into the double Riemann sum that we had previously. So basically this is the term that replaces the area of Rij. And after rearranging, we have the following expression, which in the limit converges to the following iterated integrals with respect to r and theta. Now it doesn't matter which order we use for r and theta, because both of these variables are bounded by constants. Alright, let us put our findings in the following theorem. So formally, if f is continuous on a polar rectangle R, then the double integral over R can be computed using the following iterated integrals with respect to r and theta. And here are a few things to remember when doing this conversion. First, we must replace x and y in the argument of our function by their corresponding expressions in terms of r and theta. And second, we have to make sure that the appropriate limits of integrations are used for the variables r and theta. For example, if theta is placed at the outer integral, then the limits for theta are given by alpha in the lower bound and beta in the upper bound. Whereas the limits of integrations for r are given by a in the lower bound and b in the upper bound. And finally, the term dA on the left hand side is replaced by the term r dr d theta. So do not forget the additional r when converting to polar coordinates. Alright, we shall look at some examples in subsequent videos. Stay tuned.